So it's still the Touch the Truck game. You see, it takes more time than you would have probably expected given how simple the game seemed. Except now what we try to do is we try to solve it by using the mixed strategy equilibria. The mixed strategy equilibria in the Touch the Truck game. Just a brief reminder. So the structure of the game was as follows. There was this first player who had two options, second player who had this information set. If they both keep playing the game, then they enter the second stage, and in the second stage it repeats again. Both of them have to simultaneously decide whether they want to stay or to let go, and in the end whoever is more persistent gets the prize. And the two equilibria that we found in pure strategies by solving this game using backward induction and using subgame perfection was that either it's A who stays and B who goes, and they get payoffs V for the first and 0 for the second. We call this equilibrium the blue equilibrium, right? Or it's A who goes and B who stays, and then it's vice versa, 0 for A and V for the and V for B for the second player. And the reason they are doing that is they don't want to go into the second stage, because if they go into the second stage, then there again would be these two options, either this one where A does not want to play and B plays, or another option, this one, where A plays and B does not, right? So they did not want to proceed there. They knew that there would be these two subgame equilibria there, and depending on which subgame equilibrium it would be there, for instance, if A knew that A would still be playing there, this uppermost option, then A would be just playing here, and B, knowing that, would play the blue equilibrium. Or if the other way around, A knows that in the second stage A would decide to let go, then A would decide to let go already in the first stage, and the green equilibrium would materialize. So what we try to do now is we'll find the mixed strategy equilibrium in this game. The reason we want to do so is, well, here is the intuition. So my intuition for this game is that if they knew who would persist till the end, if they knew from the very beginning who would be this person who gets the car, then yes, of course, they would not want to play, right? But there is some level of uncertainty about that. So that means that with some probabilities in each of these stages, they might want to let go or to keep touching the car. And as long as there are these probabilities involved, chances that you will want to keep playing, then there is a probability that all of the players will want to keep playing. And this is the probability that the game continues into the second stage. And I just want to remind you that we talked about how this game actually has more than two stages. So we just simplified it now, but except for the first, second stage, there would be this nth stage somewhere. And they would be able to come there if they kept staying as the actual contestants in this game do. Right, so the game would repeat and repeat and repeat itself. So maybe us thinking about this game in terms of mixed strategy equilibrium would allow us to predict how this would be possible, that they keep staying there and playing and playing and playing this game till the nth round, or maybe to infinity. To find this, but for now, of course, we return to this two-stage version of the game without thinking about how the game continues. So if they keep staying, then the payoffs that they would get let me remind you, would as follows. If they both stay, then they get minus 2c, each of them. So minus c for the first stage and another minus c for the second. They waste their time, they spend their efforts, they don't get the car. However, if one of them lets go, then this guy or girl, so for instance, A would be a girl, she would get V for winning the car minus some cost C for staying throughout the first round. And the second player, B, only gets this minus C from the first round. It's vice versa here. It's minus C for A and V minus C for B. And it's just minus C's in case they decide to let go after the second round and after having spent time in the first round. So now we repeat the same thing. We solve the game using matrices, except now we'll look for the mixed strategy equilibrium in this game. So we start with the second stage. And in the second stage, there is this matrix. No surprises. It's, I don't know, it's fourth time that I draw the matrix today. Two players, A, B, two strategies for each of them, either to stay or to go. The payoffs that we have already memorized. Minus C's if they both go, minus 2 C's if they both stay. Whoever stays gets V minus C, whoever goes gets minus C. And now we try to solve for mixed strategies. So there will be this P and Q. And 1 minus P and 1 minus Q respectively. And of course you remember how we do these calculations, but just as a matter of reminder, what we need to do is we need to set equal to one another the expected payoffs that players get from playing their pure strategies against the mixed strategy of the other player. So for instance, the first player, player A, would get payoff minus 2C with probability Q, and also the payoff V minus C with probability 1 minus Q. And these two payoffs, that one and that one, weighted with these probabilities, should be equal to these two payoffs, minus C and minus C again, weighted with probabilities Q and 1 minus Q. So basically it's minus C times Q plus minus C times 1 minus Q. Here is a cool thing to notice. This second half, the way it looks, suggests that regardless of what the other player is doing, of what value of Q player B will set, it will always be minus C for the first player, right? And we can see that in the matrix, it's always minus C. Whatever you do, if you let go, you get minus C from the first round and 0 from the second. Let's just write it down. It's always minus C. Of course, we could get the same result by opening up the bracket. So it would be minus CQ plus minus C times 1 plus minus C times minus Q. That means minus CQ plus CQ, right? And they would cancel out and we would only get minus C there. On the left-hand side of the equation, we just open up the bracket. It's minus 2CQ plus, and opening these brackets, we get V minus VQ minus C plus CQ. On the right hand side, well, let's just do this stuff. Let's open up the bracket, but we have already discussed that it should be just minus C. So it's minus CQ minus c times 1, minus c times minus q, that's plus cq. So these two things would cancel each other out. But also notice that in the left-hand side and in the right-hand side, we have this minus c. So they too would cancel out. And what we get from here is this. Minus 2cq plus v minus vq plus cq. These and these two things can be added together. So minus 2cq plus cq, that's just minus cq minus vq plus v equals 0. And then you want to express q because we are trying to find the value of q. So it will be minus q multiplied by c plus v, and it's equal to minus v, right? So we have taken this v to the other side. It's one thing. And we have taken this q, this minus q to be more precise, out of the bracket and got c plus v in the bracket. Then what we do is we cancel out these two minuses in the left and in the right hand side. And we can express q. So q equals v over c plus v, right? That's the probability q. If you look at the matrix, you will see that the players get exactly the same payoffs, right? So if we tried to calculate the value of p, we would get the same result. So check it for yourself. Check it for yourselves, but I'll just write it here. P would also be equal to v over c plus v, right? That's the mixed strategy equilibria values of p and q, the probabilities with which a and b stay in the second stage. Now what we would need to do is you have to remember that what we are trying to do is we try to find the payoffs that the players, as they play the mixed strategy equilibrium in the second stage, would get in the development where they decide to both stay. So if they both stay here, the payoffs they would get would come from the second stage of the game. And in this second stage of the game, the payoffs would be defined by these values of p and q, right? To calculate the actual values for the expected payoff that they get, you have to remember that these values are the payoffs that the players get. So for instance, player A gets minus 2c, v minus c, and minus c, multiplied by the probabilities with which each of these four cells happens in reality. So by pq here, p 1 minus q here, 1 minus p q here, and 1 minus p 1 minus q here, right? So you just take these numbers, minus 2c, v minus c, etc. And now that we know the values of p and q, and they're the same, they're v over c plus v, you just multiply this minus 2c, v minus c by pq, p1 minus q, etc. And you substitute instead of p and instead of q, substitute v over c plus v. That's one very technical way of calculating it. Another way, and this other way also provides you with the same result, is to think about the mixed strategy equilibrium in terms of what the players are trying to achieve by playing these mixed strategies. And I remind you that they try to make the other player indifferent between her two pure strategies, or more specifically, between the payoffs that the other player would get from playing her two pure strategies against your mixed strategy, right? That means that these payoffs should be the same, and when we wrote down, for instance, for the first player, when we wrote down this equation, we were making the first player indifferent between her two pure strategies, so her expected payoff from playing the mixed strategy and any of her pure strategies in this situation would be the same. And that means that this very long thing that we could calculate, minus 2c by v over c plus v squared plus v minus c by this p times 1 minus q, etc., it would have to be equal to what you would get if you just calculated the expected payoff for the first player from playing any of her pure strategies. I suggest that you pay attention to this particular one. So that's the expected payoff from playing strategy Go, because her expected payoff from going is always minus C. Think about it for a moment. And that means that her expected payoff from staying is also minus C, right? Because these are the values of Q that we have calculated. So the expected utility for player A from playing this combination of equilibrium probabilities would anyways be minus C. And that's the minus C which comes from the first stage. So in the second stage, actually, you don't lose or you don't win anything. You get a 0, right? That's what your expected payoff should be. It's just math, right? That's what math is telling us. But that means that when the first player is looking at this game, she knows that the second stage, where P and Q, these equilibrium strategies, are played, would result in her getting payoffs minus C, and zeros, right? So it's just these payoffs that she will get on average, expected payoff. And so when we look at the first stage and try to find what would be the mixed strategy equilibrium there, this is what you get. So in the first stage, again, you have this matrix, it's 2 by 2, right? What is it, like the sixth time that I draw this matrix? Now we know that if they both stay in the first stage, their expected payoffs will be minus C. These are the expected payoffs that they get in the second matrix with the probabilities PQ, right? And we know all of the other payoffs. If you stay and the other player goes, you get V versus 0. If you go and the other player stays, you get 0 and the other player V. And both of you get zeros. And then again, in the first round, we introduce letters P, letters Q, and then you do the calculations, right? So it's, for instance, if you want to calculate the value of P, then you use the second player's payoffs. It's minus C times P plus V times 1 minus P. And it should be equal, and we're talking about the second player, it should be equal to 0 times P plus 0 times 1 minus P, always a 0, right? And then solving it very quickly, minus Cp plus V minus Vp equals 0 minus P multiplied by C plus V equals minus V, P equals V over C plus V. And again, the game is symmetric, so value of Q would be the same if you calculate it. Again, check for yourselves. So what we found out is that the values of P and Q, first round, second round, they are the same. It's V over C plus V. And that means that there is this mixed strategy equilibrium in this game. Let's write it down. So in the mixed wrong way. In the mixed strategy equilibrium, what the players do is first player plays V over C plus V. That's the probability she stays in the first round. And also V over C plus V. That's the probability she stays in the second round. And the second player, player B, does the same. It's V over C plus V in the first round, and then again V over C plus V in the second. The reason this is interesting is that if we look at this game and remember that we have limited it with 2 rounds, whereas in fact it could last for more than 2 rounds, then what we see is that basically there is a probability, and actually this probability can be quite high, with which they first both play stay here, and then they keep playing stay, and in the nth round they play stay again. This probability that they both play stay in one round is P times Q. And if you multiply P by Q that we found, you'll see that it's V squared, it's V by V, over C plus V squared, right? So the probability that this will repeat in the second round is the probability that it happened once by the probability that it will happen again. So it's P times Q squared, and then it's this stuff squared. So in the nth round, what you'll get, it will be P times Q to the power of n. Basically, it's V to the power of 2n over C plus V to the power of 2n. And that's some number, right? So there is some probability that the game continues, that it goes into this nth number and possibly is played long enough for us to get bored by the game, just what happened now with us solving this game, right? Importantly, look at this probability. So the probability Q and P, V over C plus V, it's V divided by itself plus C. And if V is large enough and C is small enough, so if V is the probability that if V is the value of the car, beautiful brand new pickup truck, and C is just the cost of, standing for another 5 minutes, then of course this probability could be almost 1, right? Because it's basically V divided by itself with a little tiny bit more. And then as you take this 1 to the power of n, you almost get a 1, right? So it's almost the probability that the game continues is decreasing every next round, but it may still stay high enough if C is very little, right? If C is tiny and V is large. So this is how this game repeats itself. That's because the players do not rely on these two possible pure strategy equilibria that we found in the previous video, but because they try to play the mixed strategy equilibrium that we found now, and because in this mixed strategy equilibrium, under some conditions, when V is large and C is small, the game will continue indefinitely, right? It may last for very long hours.